Okay, welcome to our discussion on the physical properties of haloalkanes. Now, I like to discuss this first before we go into mechanisms because we can get an idea of the nature of the CX bond and the reason why these reactions undergo the way they undergo. Anyways, let's get right to this video. Well, there's three main points I want to discuss in this video, and that is bond strength and bond length, the polarity of the CX bond, and the boiling points versus their corresponding alkanes. Now, what in the world is X? X is just the symbol for halogen. So this is just halogen. And that could be fluorine, chlorine, bromine, iodine. So let's first discuss the bond strength and the bond length. Well, if I draw a carbon halogen bond, a haloalkane, and the haloalkane is just a functional group, and we should know that functional groups are the centers of reactivity in organic molecules. So let me just keep drawing this, and I'm going to draw, say, fluorine, and then I'll draw a, say, I don't know, bromine. Okay, so which bond is stronger and which bond is longer? Well, we can see the only difference is the halogen in these two bonds. And fluorine is higher up on the periodic table and is smaller. So the atomic radius is smaller. So atomic radius smaller. And this atomic radius for the bromine is much larger. Well, when our atom gets larger, our electrons are more diffuse in that orbital, and that creates a weaker overlap. So this carbon-fluorine bond is much stronger than this carbon-bromine bond. And the reason being is as our atoms get larger, the electrons are more diffuse. So let me write this down. So I'll just say large atoms, or specifically in this case, let me go back if I can. Large halogens have a weak overlap. So if we look closely at this carbon atom, what is the hybridization of it? Well, that is sp3, and it is overlapping with a p orbital on the fluorine. Now, the p orbital on the fluorine is much smaller than it would be on the bromine, and that is why the overlap is much weaker in bromine than it is in fluorine. So large halogens have a weak overlap, and that means we have weak bond. And if our bond is weak, this bond is also going to be long because this atom is much larger and it's going to have a harder time overlapping with this carbon. So we could also say weak bond and long bond. So this carbon fluorine is small in length, so I'll say small length, and strong. While this bromine is long, but it is weak. Okay, now let's move on to the polarity of the carbon-halogen bond. So halogens are much more electronegative than carbon, so it is going to get a delta minus, while the carbon is going to get a delta plus. Now, this carbon is what we call electrophilic, and it will be attacked by electron-rich species, while this halogen has a delta minus, will be attacked by cations and other electron-deficient species. So, that's really all I have to say for the polarity of the carbon-halogen bond. This will make much more sense when I start going through, say, SN1, SN2 mechanisms, but that's really it for this point right here. So I'll write delta plus attacked by nucleophilic species, while the delta minus will be attacked by cations. All right, my final point is the boiling points versus their corresponding alkanes. So what does corresponding alkanes mean? Well, this CH4 is methane, and if we remove a hydrogen and attach a halogen, that would be the corresponding haloalkane. So that is really all it means by the halogen and their corresponding alkane. So if we just look at these first two, CH4 and CH3F, we see that CH3F has a higher boiling point, while methane, CH4, is much more lower. And what could be the reason for that? Well, in a solution in the liquid state, remember intermolecular forces, and that the polarity of that carbon-halogen bond allows it to go through dipole-dipole. So let me write that down. Dipole-dipole. And let me draw this in a liquid state. So I don't know why I drew that as a hydrogen, but let me remove that. Fluorine. And this fluorine has delta minus, it's more electronegative, and this carbon is delta plus. So let's draw another molecule, because in liquid state we have all these molecules around. So we have another, I'm going to draw the carbon here. Hydrogen, hydrogen, delta plus, and hydrogen and fluorine, delta minus. Now this delta plus will be attracted to this delta minus, so I'll draw a little dashed line to indicate an intermolecular force, and that is why the CH3F has a higher boiling point than CH4. It's because of those dipole-dipole interactions. Now, if we look at CH3 or CH3F versus CH3I, CH3I has a way bigger boiling point. Now, why is that? Well, the only difference between these two halogens is iodine is much larger than fluorine. Now, why is this? The reason why iodine is much larger than fluorine is because it contains more electrons, more shells, but that's not really important. What's important is when atoms are larger, they have more London dispersion forces. So I'll write that, say, right here. I'll say larger atom, more London dispersion forces. So CH3I has a higher boiling point than CH3F because it is a larger atom, which allows it to have more London dispersion forces. Once again, we're just talking about intermolecular forces. Now, this does it for this video. I hope to give you a somewhat of an understanding of physical properties of the haloalkanes. Now let's get into SN1, SN2 mechanisms.